Okay, so hi, I'm Steve. I've been at Elastic since 2016, and I work in sort of the machine learning area, but also more recently sort of across Kibana and response ops and some other areas in the engineering group as well. And what I'd like to go through quickly, I know everyone wants beer, pizza and football tonight, but I'd like to go through a bit about semantic search, but also sort of give you some insights into how we're thinking about it from an engineering point of view on the back end and how we're approaching the problem. And because this is more of a meetup talk than sort of an official customer talk we'd give at Elasticon, so I can dig a bit into sort of the engineering process and some of the things we're doing. Okay, so I know, have we got any information retrieval PhDs here? Okay, good. Well, so what I'm going to talk about is fairly high level, but I'm going to talk about semantic search. Now, semantic search itself is a pretty fuzzy term that can mean lots of different things, but really what I'm talking about is textual search in this context, and the examples I'm going to give are specifically about textual search. If you're at Elasticon tomorrow, I'm going to give some examples that are actually image search and so on, but tonight I'm going to focus more on textual search. And really, when we talk about semantic search, we're trying to retrieve results that are based on the user's intent and contextual meaning, rather than just the keywords they've put in the search query. So if I search for something like how to set up Elasticsearch ML meaning machine learning, then instead of just searching for those keywords across a set of documents, I might want to search for sort of related terms, related context. Like if I say how to set up, I might also be interested in pages which say configuring Elasticsearch ML or installing Elasticsearch or ML or getting started or settings. As it's Elasticsearch, I might want to focus on the documents on elastic.co. ML is a synonym for machine learning, and Elasticsearch ML came from a company called Prelert. I founded, so I'm still proud of it, but was specialized in anomaly detection. So really, when you're searching for this, the user's intent is not just to search for these words, but to try and get an answer to that question. And that involves doing things like looking at potentially terms like this that are associated with it. Okay, so just to give you an example, I know this is hard to see, but I'll talk through it for you at the back. I've got some examples of how keyword search results differ from semantic search results. And in particular, as I said in the sort of the description of this talk, sort of Google is obviously a really good example of semantic search, and also something that, people are now very familiar with. And, it's sort of like something that we aspire to, giving that experience in some ways anyway. So if I'm just doing keyword search and I'm searching for how to set up Elasticsearch ML, I get these results. And this is actually just the documents from the Elastic website. I get some information about sizing Elasticsearch machine learning, which is a very specific thing about Elasticsearch aggregations for machine learning jobs, something about how we auto-scale Elasticsearch machine learning in the cloud, and at the bottom here, something about deployment templates, which isn't actually that related. And we do highlight the keywords we've selected, but you see that things like setup haven't been joined. So we've got things which are like up and how and so on. And it's very much like there is some relevance to these results, but it's not really answering the question that we're interested in. Now, if we search with Google, we get actually a pretty good experience here, because we get like first thing, machine learning settings in Elasticsearch, set up machine learning features, Elastic, getting started with machine learning, getting started with anomaly detection, like good results. Yeah. So like how have they done this, and how can we sort of drive towards a more semantic type search set of results? So before sort of approaching this, we thought, well, like Elastic can often be a real toolbox with lots of different things, and we have lots of different use cases, and that's a sort of a great feature of the platform we're building. But one thing that we were thinking about, and in particular working with our enterprise search team, is how to make this simple. There's a lot of complexity in terms of deploying machine learning models, creating vectors, searching vectors, and so on. And so one of the things that we were thinking about as an objective here is, like, we should think about this is something that you could turn on And instead of us just searching for keywords, we could return results and text, which is a bit more semantic to the meaning of the words. So there's lots of use cases for what we're doing here, but really we're sort of thinking about, can we make an easy button to give you this type of search? So how do you do this? Well, at the moment, there are in Elastic, for those who have worked in search relevance, there's a ton of stuff you can do to make search relevance better now. And a lot of that is to do with text analyzers, tokenization, stemming, etc., adding synonyms, playing around with different ranking functions. Any of you have heard of BM25 is the default ranking function we use, which is pretty effective. And there's fuzzy queries and all sorts of things that we can do to make search relevance better. But it's a very manual process. And once you start adding a lot of these things together, it becomes quite complex to actually understand the predictability of the results and so on. But you can certainly get improved relevance by tuning these things. However, there's a lot more modern way of doing this. And this is sort of the way that we're adopting and have been adopting over the last few years with bits of technology. The first thing is that we take the documents and we transform them using a machine learning model. And I'll go into a bit more detail about that, into a set of embeddings. Now, these embeddings are generally vectors. So you can imagine that I've got a document and I transform that document into a numeric vector. And those vectors can be, say, 500 dimensions or even more, depending on the models. And that is what we index. And that vector actually is actually a representation of that document. Now, when we do a query, we take a query, we create a vector using the same model, we create a vector which represents the query, and then we search, instead of searching the text space with the keywords, we actually search the vector space. So you can imagine that we've created this representation of the text, and we're actually trying to search in that space as opposed to the text space to return the results. And that then gives us the relevant documents. And the advantage of searching in the vector space is that you're no longer constrained to just searching for the keywords, but you can search for actual similar expressions. And if there's a, going into what these models are actually doing, there's actually a lot of intelligence in terms of matching context and contextual terms and words in terms of how you can match these vectors. Okay, so, but there's a big caveat. I've got to remember to say this, right? This, like you look at blogs on NLP, you look blogs on this stuff, and there's lots of examples of people just taking, say, BERT models, doing transfer learning using MS Marco data sets, and they go, there you go, you've got relevant results. But that doesn't work in general, yeah. And what we're trying to do is find a general way of improving search. And there's a lot of information saying how easy this is, but actually it's quite hard to get generally good results. Okay, so when we were looking at this, obviously, we wanted to look at, well, what things are people using? What things are people using at the moment that work well? And also, like, how can we come up with a generally useful method, and how can we evaluate a generally useful method? So in this case, we're not giving you a toolkit which says, go at it, put whatever model you want in, you'll use these embeddings and do stuff. We want to try and give you a proven solution for improving your search using semantic search. And then also, like, there's lots of things that you could do. You could do these cross encoders that would require days of GPU time to actually get any results. But we want it to be compatible with the Elastic stack and to give you results in the same sort of timely manner that Elastic does at the moment. Okay, so there's a lot going on in this research field. So BM25, which is what Elasticsearch is sort of currently based on, 1976 was the first paper I found on that. So that's been around for quite a long, and it can be, no, it still works very effectively, but it is quite a traditional information retrieval method. Now, more recently, particularly in 2019, there was a big spike in the results people were getting in terms of these big relevance benchmarks. And that was because Google released this model called BERT. And basically what Google did, they took the whole of Wikipedia, they took most of the Google Books corpus, and they used all of that to create an unsupervised model which effectively embeds the sort of general understanding of language in that model in some ways anyway. So, like, and they're giving it away for free. It's open source, you can use it, which is great, it's fantastic. And since then, that model has and training on top of that model has been used to basically beat relevance benchmarks across the board in different domains. And more recently, there's actually sort of these variants of cross-encoder type models that have come up, and even like this Splade model and Colbert and so on are outperforming some of the prior art as well. And you know, this is really recent. This is sort of in the last year these things have been coming up, and they're looking really good. So you know, it's actually a really good time for us to be doing this, because there's actually a lot of research which is working really well, and certainly a lot better than it was a couple of years ago. Okay, so in terms of what we're doing, this is sort of just a quick outline. Again, I don't want to take up too much time, but in terms of this is going sort of through the approach we've taken, the different sort of iterations of going through what we've been doing, and then sort of the conclusion. And remember, the goal here is to try and come up with a general purpose tick box for semantic search. Okay, so a key thing with us doing this and trying to release something that's generally useful is we want to benchmark it, and you know, as we're developing this, prove this against as wide a range of data sets as we've got in terms of actually showing that these results are good. And the good thing is there's actually quite a lot of benchmarks available, because you know, to evaluate search relevance, what you need is a lot of documents, you need a lot of queries, and you need someone who's marked up results from that to say this is what this query should return. And that's a very expensive process. But you know, Microsoft released this a while ago, which is sort of a classic set. It's, you know, it's almost 9 million documents, 7,000 labeled queries, and it's real queries sampled from Bing, and it has sort of query and the results that query, you know, good results for that query. So that's an example of a marked up data set, and our goal is to get really good results on these type of benchmarks. So we can sort of replicate, if you query for this on this data, we should hopefully return this, you know, very high up in terms of the sets of documents we return. Now, to give you an example of like how much the research field has moved on, like there's scores you use. So you basically, you know, run all these queries, you do all these tests, and at the end of it, you can get a score. And there's different scores. And like, I can talk to you afterwards if you're interested about what the different scores are. But like, for instance, BM25 gets a score of 0.19, almost 0.2. State of the art gets 0.45. So state of the art is sort of twice as good in terms of returning results. And state of the art is based on machine learning, cross encoders, etc. In terms of returning results. So state of the art is a lot better than BM25. Okay, so in terms of what we did, like we took around 28 domain data sets. There's actually 2 big research projects that are sort of consolidated across the information retrieval sort of academic groups. One called Beer, one called Lotta, and there's, you know, there's a lot of data there, and you know, there is variety in them because different domains are different. You probably can't see this, but this is a selection of them. You've got data sets based on finance, biomedical, Wikipedia, scientific data, miscellaneous, and you know, they've got millions of documents, you know, sort of thousands of queries on some of them and so on. And so there's a lot of work gone into constructing this set of benchmarks. And you know, our goal is to say, well, look, if we can get as many benchmarks working as we can, then we've got a lot more confidence in terms of supplying you with a feature that's likely to give you better results than we've got currently. Now, there's one sort of technical point here that's key, and that is when you get these machine learning models, you often train them on a data set. And a lot of them are trained on that MS Marco data set of those 9 million documents. Now, the problem is that if you then use that to evaluate your results on MS Marco, you'll get good results on MS Marco because you've trained it on queries and results from MS Marco. So it's sort of, it's not quite marking your own homework, but it's something in domain. Whereas, you know, what we want to do is look at, well, we'll take a model and we'll evaluate it out of domain. So not on the same data that we've trained it, not on the same data or the same data set that we've trained it on. We want to evaluate it out of the domain there. And that's sort of a key thing, because that's where a lot of these techniques don't work very effectively, is that they're trained on a particular data set, and then you transfer them to a different domain, say biomedical, and they don't work particularly well. So a key thing here is we're doing it out of domain. And this is just like we picked a particular ranking metric because that's the metric that the academics are using for a lot of these benchmarks. Okay, so this is going to be too small for you to read, but this is just a subset of the data sets, and BM25 gets a score of 0.417, which is actually pretty good. And this is our baseline, because we could go to a lot of complexity, we could add all this functionality, and if we don't do better than we are currently, it's not a particularly useful product. It's just a more expensive product in terms of compute view. So we want to try and get better than that baseline. So the first thing we do is called dense retrieval, which is this, where we're taking the documents, we're using machine learning model, we're creating a set of vectors and so on. And it really comes down to the choice of machine learning model you use in this case. And like, as I said earlier, the key thing is that you start off with this BERT model in general, and then you train it, you specialize it on a specific task. So in this case, generally you specialize it based on going from queries to results. And that's what you train this on. And generally, if you use, there's a specific set of data you use to do this training. So the results of this, and this is really bad color choice because I'm red-green colorblind. So, but basically, we've gone to all this effort, we've been creating these embeddings, and these results are worse than BM25. So we've got standard elastic, we've created all these embeddings using these fancy models, and these results are worse. So if we just take those and say, okay, here you go, look at some blogs, download these models, try this out, you get worse results than Elastic does now. So that's not a good solution for us just to have a click. So what can we do? So one thing we can do is that, we can, in Elastic, we can actually get results from BM25 and from the dense model. And what we can do is potentially combine those together and create some sort of hybrid method. And there's different ways of combining it. We can combine them in a linear sense. And we can also use something which is a little bit better, which is called reciprocal rank fusion, where we're looking at basically combining results from standard Elasticsearch and from these vector embeddings. Now, the cool thing is that doing that, even though these dense models on their own aren't good, if you combine them with one of these combination methods, the results are better. So we've gone from 0.147 to 0.45 about there with reciprocal rank fusion, which is actually, in the grand scheme, it's actually quite a good step up in terms of when you actually look at the results. So that's really hopeful. So and this is something that we're actually pretty close to shipping now in terms of you having the ability in 8.6 will have the ability to do this in a linear hybrid sense. And so this is something where you can actually get a better semantic search method in a pretty reliable sense across these benchmarks than standard Elastic. However, there's more, and this is sort of like one of the key areas that we're really digging into at the moment, is these things called late interaction models. And these work in a bit of a different way. These are, if any of you are familiar, these are cross encoders. So they're actually a lot sort of more complicated, and these beat everything. So they're called these sparse expansion late interaction models, and these beat Fusion, they beat BM25, and they work generally across all these data sets, 0 shots. So they've been trained. Actually, the one we used there was actually trained on MS Marco, but with all these other data sets, it's outperformed everything and looks really good. So if we can shrink wrap that up, it'll actually give you a nice semantic search experience out of the box. And the other thing, again, this is probably too small to read, it works in a different way in that it actually has other benefits in that it's not actually encoding a vector. but it's actually taking the document and creating the list of tuples where each word has a weight according to how important it is in terms of potential matches. And it also adds new terms, which are synonym terms, and it drops terms as well. So we're effectively like doing almost automatic weighted synonym extraction from the original documents and queries. And that is what we can match against. And the cool thing is that it's actually quite native to Elasticsearch to be doing that type of matching, because it's a bit like TF-IDF. But there's also, it's a bit more intuitive, because instead of looking at a vector, you can actually see how we're expanding things. We can also highlight the relevant terms and highlight the synonyms and so on. So, we're really excited about this, and we're actually developing a particular method here, and we'll hopefully write some academic papers on it as well, because I think it's quite a cool approach. Okay, so I went through that really fast, but I just wanted to go through like a bit of reality and actually show you some of this in product, because it's not all PowerPoint. So unfortunately, okay. So one thing is you need to get so at the moment we have the ability to upload these large language models into an Elasticsearch cluster, and for you to then perform inference on those, basically transform documents to vectors, and then do vector searches across those using efficient searches. So the first thing we can do is we can upload a model. We've got a Python library called Eland. So we're near Eland's correct and everything. And there's just basically a simple script where you can take a model directly from Hugging Face and upload it into an Elasticsearch cluster for use. So in this case, I've taken a model, and this model is actually a sentence transformer model, which takes text, transforms it into a vector, and can work fairly effectively. And that is now deployed and running in my Elastic Cloud cluster. I've then indexed the documents, and I've indexed the documents through an ingest pipeline. So this is all native Elastic code. And as I index them through an ingest pipeline, the text here gets transformed into this vector. And so this vector here represents this text. Now, what I can now do is search. Now, I can search this using conventional search. So I've got a query here saying, does being vegetarian help the environment? And the first answer I get is to do with actually sort of more is the problems with fatigue, apathetic behavior, and concentration, and mostly the result from a lack of iron in the diet. So it is relevant to being a vegetarian, but it's not necessarily answering the question. Whereas what I can also do here is I can do a search where I'm searching in the vector space rather than directly in the text space. And this is a new endpoint called Semantic Search that we're releasing in 8.6. And when I search in this space, the first result is about you don't have to be a vegetarian to be green. Many special environments have created for livestock farming, etc. So it is actually more relevant to that particular question. I know I've picked a specific question, but you can see that you're getting different results, and those different results are due to the fact that we're searching the vector space as opposed to the text space. And then finally, one really cool thing is we've got a way of doing a hybrid search, and again, this is an 8.6, where we can combine text and vector searches together and produce a combined result with your own boosting weights as well, which again sort of gives you some volts, which is sort of a hybrid of the two. But in this case, I'm weighting the vector higher. So there's a lot of content there. There's a lot of probably some technical stuff there if you're not familiar with machine learning and vectors. But hopefully, this will give you the sense that we're trying to make semantic search more of a reality for users of the Elastic Stack. And in particular, we're trying to do it in a way where we're confident that we'll give you a good experience on your data sets, as opposed to potentially just a toolkit where you have to upload your own models and so on. That's all I've got, and happy to answer questions. Yeah.
You mentioned that you're using a multitude of models covering different scopes, domains. Question: to what degree are those language agnostic, or is this all about English?
Yeah, so the current benchmarks we're running are in English. We can certainly use multilingual models as well, and they actually work in a very similar way. The only issue would be we would need a training set in that language to create that model, and there is availability in certain languages. Dutch, it's a bit limited, but there are some training sets available.
Just to follow up, we've actually done the work to translate MS Marco into 13 languages, so there is an MS Marco for Dutch.
Perfect.
I can tell you about it.
Well, I mean, in that case, we can certainly, we can train a model based on a multilingual bird with a Dutch MS Marco, and replicate and particularly the training step, that pre-training step, particularly for the sparse interaction models, is something that we're developing the code, and we're going to make the code public about. So that's something that we could use a model and even publish that model openly as well.
I had a different question, actually. So you talked about hybrid search, combining, let's say, classical boosting signals with the vector similarity scores. What's kind of your tips and tricks for that? Because it seems like the vector search bandwidth of or like the expressive range of those similarities is very small.
Yeah.
So it's very hard in practice to boost them with like a classical signal.
So with a linear combination, where what you've got, the parameters that you can set are alpha in terms of just the boosting weights that you can combine them with, but there's also the scores are normalized differently in the different domains as well. So to combine them linearly in an effective manner, like you either tune the alpha for the data set, which requires you to have markup, or you have to have a normalization strategy that's consistent, and then you can use a consistent alpha. However, my advice is that the linear combination can be quite tricky to tune, and the reciprocal rank fusion works a lot more effectively in the general case. And the single parameter k there, you can fix at around 20, and it seems to work across all the data sets out of domain. So I think in terms of like the simple combination techniques, I think reciprocal rank fusion seems most effective generally without a lot of tuning.
Question: what's the model? Because you need to transfer the model from the training results and to the Elasticsearch. The model file an open format, or
yeah. So the models are like, so if you go to like Hugging Face or one of these model repositories, there's a load of models there, and you can basically just take those and directly upload them into, like here we're taking just this is a particular model that we actually published on Hugging Face, but you can take any of these models. Like for instance, I could just take that's there, run that Python command, and provided I had my configuration for my Elastic domain there, it would be uploaded directly. And like that internally, what's going on is whilst Elasticsearch is written in Java, the machine learning parts are C++, and we're actually doing PyTorch inference there. So we actually have the PyTorch libraries, and we can embed the PyTorch models there.
Technical question: did you use the rank-eval API to calculate the metric?
I would have to check with the team on how they did it. The beer framework has that pretty much all built in. So we used I think we used that and basically adapted that with new test cases. I think it's a really nice framework for doing the whole thing in. And those benchmarks, the majority of them were done outside of Elasticsearch, the actual testing, because we're, our R&D, it can be done a lot more effectively and quicker in Python, and then we can transfer it into a production Elasticsearch environment.
The models Google uses, will they ever be outsourced to the Dutch language?
The multilingual variants, well, correct me if I'm wrong, but they are in Dutch as well. Yeah.
Yeah, but they're not as accurate as Google itself.
You mean the translate? Yeah, the translate isn't very good, but this is, I think, if the BERT models fine-tuned on Marco for a specific language, could be good. Again, it's something that we could do actually, is we could run a similar set of benchmarks with Dutch, in Dutch and see.